Don't see him yet. I will call him in.
Thank you.
He's still not in. Maybe he's got an issue. Yesterday he was fine. Yeah.
Do you have Angela's contacts?
He just sent me a message that he's just in. He has to be in a committee. So maybe just proceed.
What did he say, Bjorn?
I just got a message that he is in a meeting at the moment. I'm sure this is an urgent meeting that he is in. So if you could just proceed.
Okay. Noted, Bjorn. So it will mean that we will not have a presentation on the role of standards at the moment, but Dr. Bison will join us later on, whereby he will do the presentation on the role of standards in South Africa. So I would officially welcome all of you to the webinar and wish you all of the best and a productive webinar for the day. Without a waste of time, I'll move on to the next item on the program, which is the topic around the creation of new nanotechnology industries, which will be done by Nontombi Marule from the DTI. If you look into on the program, there was a presentation to be done by Dr. Xolani Makhoba, but unfortunately, he couldn't make it to the session. So we just skipped that one and moved on to the next, which is the creation of the new nanotechnology industry, which will be done by Nontombi Marule from the DTI. Over to you, Nontombi.
Okay, good morning, colleagues. Let me just find my presentation. Let me know if you can see it.
Yes, Nontombi, I can see from my side.
Okay, perfect. Is it on full screen?
Yes,
perfect. All right, all right. Good morning then, colleagues. As already introduced, my name is Nontombi Marule, and I think I'm just a bit ruffled by being the first speaker. I thought I was going to be the third one.
Sorry about that.
But anyway, it's fine. I'm just going to unpack because some of my presentation estimated. So there's information I didn't put on my presentation preempting that Xolani would have talked about some of the things, but I hope that when he comes in, it's all going to come together, or so that you can see where we are at. I'm going to do the best that I can under the circumstances. And thank you for the opportunity. I'm just looking at the time so that I can time myself. Thank you for the opportunity, and it is my pleasure to be here and sharing our work within the DTIC with you in terms of what is our strategy to then create new industries. Our theme is more on new industries in general, and you'll see in my presentation why I specifically say new industries are not necessarily nano, but because I'm very well au fait with nanotechnology, I've worked with it at the DSI in the past and I know where the developments are at, it makes it easier for me to then transcend into that. So this is how I'm going to roll out my presentation in terms of what is the role of the DTIC, what do we do within the Innovation and Technology unit within the DTIC so that you get an understanding, how we look at the innovation process, how we look at this concept of creation of new industries. I'm going to introduce a few of some of our incentives that we use, which I will implore our participants to then go to our website and look these incentives up. I didn't go into task in terms of the incentives because of time constraints, and also because I feel like everywhere I've done presentations about the DTIC, I talk about the incentives. So those could be easily looked up, and then I'll conclude my presentation. Now, moving right along, the DTIC basically, what we are mandated to do as a government department is industrial development, industries that should be globally competitive. And whilst we are doing that, we are employed to make sure that we create inclusive growth with the understanding of where South Africa comes from in terms of economic development. We create decent employment and equity as we do this industrial development. Now, our mission basically is on structural transformation. And this is both spatially and in terms of groups. We then also are to increase competitive and provide an environment that will render our industries competitive, equitable, and then create a social responsible environment responding to environmental global stances. Also, create an environment that is conducive to investment, trade, and enterprise development whilst we drive this industrialization agenda. But more importantly as well, we broaden the participation of the economy for all the previously disadvantaged groups, individuals, and economies. Now, one of the main guiding documents for us is a national industrial policy framework, which is sort of our guiding document or a Bible within the DTIC we sing from, or the hymn book which we sing from, where things like labor absorbing industrialization path are very pertinent, inclusive industrial growth path, economic development, and designated industrial development in areas where we've seen a decline. Now, my unit in particular, innovation and technology, is structured such that we drive any knowledge form to create industrialization or economic activities. And I always, make this joke that if you come to the DTIC, we are actually called the DSI of the DTIC because all technology development that needs to be done to drive industrialization happens in our center. And as such, we bridge the gap where either it's research, development, or any knowledge forms into, instruments like enterprise development, new industries, or current or existing industry development. We also work very closely because if you can imagine, this space that we're operating in is that a space where we are looking at all forms of instruments and tools that are used to convert those knowledge forms. I'm going to go into them as in the next slides, but basically we are that bridge that ensures that we can draw R&D, technology, innovation, and make sure that we create industries in that form. Now, if you look at the innovation process, this, I must say, is just a simplistic way of just looking at what innovation process is about and where we are at. What we have tried to do with this slide is just to show the continuum of how you move from basic and applied research or any knowledge form. Could be indigenous knowledge, it could be garage innovation, it could be grassroots innovation, and how you then proceed up until you get to market entry and market development. And you'll see that in that middle part, then that's where you have your technology development activities, technology and market validation, product and development, product development, and issues of small scale and large scale manufacturing, if it's a product. But if it's a process, obviously it's different. But this just serves as a visual form of what innovation process may look like. Now, when you look at where the DSI is focused on the innovation policy, your outputs then become proof of principles, publications, proof of concepts, and intellectual property. And from the industrial policy point of view, that's where you then have business startups, business and industry growth, new industries and import replacements. We also have aspects like export promotion and things like that. And these are typically how both of different departments or the two policy orientations will then be driving, where the industrial policy will try and pull the market, the technologies, and the innovation policy will try and push. And in the middle there, you then have pre-commercialization and commercialization strategies, which is the core of what our unit does. Now, this I'll go through very quickly because I understand that people in the attendees of this workshop understand this process very well. Technology, design and interactivity, manufacturing, business, organizational behavior, which are all critical ingredients of how you innovate, where you have the combination of the three. That's where true innovation happens, and that's where you will build these new product processes and technologies. Now, what I tried to do with this slide is just to show how different, especially DSI and DTIT, will look in terms of the approach. I've just made a few examples in terms of where DSI will come from. We'll look from a technology development perspective, where they drive nanotechnology, photonics, biotechnology, hydrogen. There's quite a number. I've just put those as examples. However, there's then a different orientation when you look from the DTIC's point of view, in a sense that we look at development of economy from a sector focus. And currently, the DTIC is very much involved in developing master plans, sector master plans, where they will dictate what are the things that needed to be done on the ground to advance that particular sector, what kinds of technologies you need to draw from the development point of view that will drive that sector, what kinds of instruments you need to put in to drive that particular sector. And as a result, you find that there's always where there's a de-link, so to speak, or a misalignment, or where we are not really finding each other. We're moving in parallel, because if you look from the technology perspective of technology approach, most of the technologies that I've put there can effectively be very relevant for any of the sectors that I've put there. However, how then we develop roadmaps and commercialization strategies around that, it's where we 9 out of 10 times, I think, miss each other. Now, from the DTIC's perspective, what we usually drive is around product and process innovation, And most companies we support are under product innovation because we drive our industrialization policy is anchored around, we said, more labor absorbing industries, and as such manufacturing becomes the anchor of what we're driving within the GTIC. Now, some of the instruments that we use include the Support Program for Industrial Innovation, the Technology for Human and Research Innovation Program, the Quebo Innovation and Industrial Program. As previously indicated, I did not go into task in explaining what these incentives do, because I believe the information is on our website, and colleagues can just go there and find out. However, we can have a further discussion if you need me to unpack them a little bit more. But one of the other incentives that we have put in place in the drive of this commercialization aspect and moving towards creation of new industries is the strengthening of incubation centers and centers of excellence, is the establishment of transfer forums, where already we are working together with the DSI, with NIPMO, with CIPC, and tech transfer offices, just to make sure that we are very clear in terms of the intellectual property portfolio that comes out of them, and that becomes ready for commercialization, even if it's licensing or in cooperation in new industry, in existing industries, or creation of new industries, is some of the activities that we are already doing. We are also actively pursuing and encouraging triple helix partnerships and quadru. I'm not sure how to say this, but those other helixes that are coming up, to ensure that whatever it is that we do is all encompassing. So we also lead, government lead as with business to seek solution. That is where we are then drawing in terms of venture capital and early venture funding that needs to be infused into some of these businesses as they are developing these particular technologies. One of the good programs that has really come out of TIA and DSI through their innovation fund is venture. It's venture capital fund for early technology development, which is quite exciting, and it's one of those things that I hoped Polani would have talked about. Now, also, stances of the DTIC is also to build the SME around large firms. This is through the programs of BEE accreditation. These are through the programs of supplier chain development management, and also development of entrepreneurship education program, which has become a mandate of universities and TVET colleges for upskilling in this area. Now, I borrowed this slide from the CSIR, and I know they are going to be doing a presentation later on. But this one, I wanted to use it just to show how well mapped is their technology and innovation for manufacturing capabilities, and how we are aligning all our incentives or our activities to make sure that at any given stage, whether it's at advanced materials development, at parts fabrication, at assemblies, we map those activities with the incentives that the DTIC offers to ensure that we are able to respond to some of what our technology development agencies are working on. Now, as I draw to my conclusion, I would like to introduce one other concept that is targeted very strategically towards new industries, driving commercialization and creating of new industries, which we call them catapults. This is a concept that we borrowed from the UK. we have, through our international collaboration, we are working with them in terms of making sure that we can drive industries from a technology orientation strategically by creating these catapults where a number of organizations can come together under one bracket of a catapult, and driven by an anchor company that will then be part of the funding mechanism, but also of the driving of the agenda and production outputs from that catapult. And you'll have instruments like your special economic zones, your industrial zones, SMME driving modalities, academia and development agencies coming together as strategic partners in this one catapult. But what then you find as activities under that is conversion of research, is investors coming in, equipment and machinery for research development and for production, internship, research labs, prototyping centers, and at the end, what you are then looking to see is creation of those new industries and also incubation and skill centers. And whilst you are developing industrial technologists, you are also developing entrepreneurs in residence while supporting the companies that become an anchor in terms of absorption of the outputs that come from that from the activities of the SMMEs in that area. I think this is where my presentation ends, and I conclude with Henry Ford's words saying, if we come together, it's just the beginning, but if we keep together, we are progressing towards a specific goal, and if we continue to work together, it's success. I thank you.
Thank you very much, Nontombi, for the information shared. Without a waste of time, we will move on to our next speaker, which is NIMISA by Dr. Clive Oliphant. We have 3 speakers there under one topic. The topic is different techniques for characterization and measurements, including device manufacturing and advanced materials, which will be covered by Dr. Clive Oliphant from NIMISA, Prof. Ray Suprikas, Dr. Thomas Malwela, and Dr. Manfred Scriba from CSIR. We also have Prof. Lakish Kwilvilu from MinTech. We will start with Dr. Clive Oliphant. The floor is yours, Dr. Clive.
Good morning, colleagues. Can you hear me? I just want to confirm if I'm audible.
Yes, Dr. Clive, you
Okay.
are.
Thank you. I'm also going to share my screen now. Can you please confirm if you can see it in full screen mode?
Yes. Yes.
Okay. So then I can get right to it. Thank you so much. Good morning, colleagues. Good morning, everyone. My name is Dr. Clive Oliphant, and I'm from the National Metrology Institute of South Africa, the NMISA or NIMISA. And I'm grateful to give you this short presentation about some of the activities that we do in support of advanced materials and advanced manufacturing. I'm also grateful for jumping off from what Ntombi just said, as NIMISA also falls within the same family there. So we're just going to build on that as well. But this will be a slightly more technical spin, and some of the examples will be shown from industry, which we were allowed, and we thank them for allowing us to show some examples there. So let me jump right into it. This is an outlay of the presentation. I will start with a brief overview of what NIMISA is, and then of course what NIMISA materials characterization is about, and then we'll end the presentation with some examples of advanced materials and advanced manufacturing, etc. Just minimize that. Okay, so on this side here, we have basically the summary in a way of this presentation. We have advanced manufacturing techniques. This is a chemical vapor deposition system where you can load some substrate in here, then move it from chamber to chamber, And then at the end, you have a complete solar cell or a complete display screen, etc. So this is advanced manufacturing processes. And down here, this is sort of materials one can make. These are nanoparticles that were used in an inter-laboratory comparison, an international inter-laboratory comparison about the size, measuring the size of nanoparticles using advanced measurement techniques. So advanced materials, advanced manufacturing techniques, and advanced materials characterization techniques. At NAMISA, we believe they go hand in hand. However, doesn't matter if it's advanced materials or any other material. This quote by Lord Kelvin holds true for all scientists, or all scientific principles and activities. When you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, knowledge is of a meager and unsatisfactory kind. That's true by Lord Kelvin, and it's especially true for advanced materials, even though we're still scratching our heads about it and how to standardize it. There is a lot of room for us there to grow and a very good opportunity for South Africa's industries. So building on that, what is the NMISA? So the NAMISA is mandated by law, by South African law, to provide for the use of measurement units of the international system of units, the SI, and other units such as the Pascal or the Newton. So basically what that means is we realize the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. So all of these 7 SI units are realized and maintained at the NMISA, and we then provide traceability to them for industries and academia through calibrations and other services. So we also then compare these standards with other national labs, such as the NIST in the USA or PTB in Germany or NPL in the UK, to ensure that all measurements in South Africa is ultimately comparable with the rest of the world, which is important for removing barriers to trade. All of our results, since we have the SI units based here at NAMISA, in any South African court, if there's a measurement dispute that needs to be settled, NAMISA's result will be accepted as the final, because of the fact that we have the SI units here and we're measuring it directly against them. And also we have compared them internationally. So there is this chain of traceability throughout NAMISA's activities. In material science or advanced materials characterization, traceability can be either to the mole, the kilogram, the meter, the Kelvin, the candela, second, or the ampere. All 7 units, basically. So materials, advanced materials, it's quite unique in that it really cuts across all these sort of SI units, and NAMISA provide traceability to those equipment that is used to measure these the advanced material properties. And of course, we can easily develop it depending on what South Africa's industry wants. So from a barrier to trade question, NAMISA is working closely with the likes of SABS, SANAS, or South African National Accreditation System, and the NRCS regulation body to ensure that we implement a competent measurement and quality control system for South Africa that at the end of the day ensure that we can sell our products or remove technical barriers to trade to the rest of the world. We fall under the DTIC, Department of Trade, Industry and Competition, and we are grateful to work with our sister institutes in achieving this goal of always trying to remove that technical barriers to trade. Now coming down to materials characterization section in NAMISA. What's materials characterization? Well, at the very basic point, it's probing the composition and microstructure properties of materials. We believe that these 2 properties influence the actual optoelectronic or mechanical properties of materials and their eventual application, their performance, their stability. So by probing these 2 very accurately, very reliably, we are then able to provide or to gain information about how to use these materials for industry and for improving the lives of all South Africans ultimately. So I mentioned previously that we use advanced characterization techniques for advanced materials. This is one of them. It's the X-ray photoelectron spectroscopy. It looks like a robot. It's quite cool. Looks like a motorcycle. But this is a ultra high vacuum chamber, as we require that to be able to perform this measurement. This is the method of choice, or in fact, it is the best metrological method to determine the thickness of coatings quantitatively. There's no other technique from a metrological point of view that comes close to this. It's a bankable technique, and it's one of our main workhorse equipment here at NAMISA. It provides quantitative analysis of the first few nanometers of interfaces of surfaces, powders, nanomaterials, etc. The time of flight secondary ion mass spectroscopy, it's right next to the XPS. You can see there it is at the back. This machine, on the other hand, is very sensitive, but it's not as quantifiable, but it still excels at getting parts per billion even of impurities in materials, which is quite important for a wide variety of industries. It can even probe hydrogen, which can be present in pipes that is used to transport hydrogen or that is used to store hydrogen. So this is one of those techniques that's quite helpful for industry. Moving on to the much better known windowless or energy dispersive X-ray spectroscopy, EDS. We have the windowless version as well, called the Extreme. And this technique removes the window that's usually from the traditional EDS detectors. That basically allows us now to probe down to the nanometer level. This is a nanoparticle that we can now accurately map, which is quite helpful for many material scientists and industries that want to use these small or these nano-sized objects in their products. We also have a focused ion beam, scanning electron microscope, the FIPSEM. This is for high-resolution microstructural features, and it has a wide array of detectors, including the previously mentioned windowless detector that can extract microstructural properties from materials. Of course, bulk structure is also important. The X-ray diffraction machine is a proven technology for use in advanced materials. And at NAMISA, we have this operated and traceable to the ICDD for highly reliable, traceable analysis of materials. So moving on to examples where NAMISA support industries. This is a additive manufacturing process where 3D titanium is printed using the lens system at the NLC, which we have been working with for many years now, since its inception. That just shows the part being printed there. And this is an electron backscatter / EDS layered image of the material that's produced there. It has these crystals in it. All of these colors correspond to how the crystals are orientated, and that influences how this material performs. So from an industrial point of view, this technology is being developed to show that it can produce materials that are equivalent to the traditionally proven casting technology, for example, of producing these sort of metals. And the advanced materials characterization then is required to confirm that. On the right here, these two images basically show you the microstrain or the local misorientation map of a sample. This shows how where there are perhaps some points where material failure can occur. These red spots are highly strained regions. Also, if you look closely in here, there's some discoloration in there. So this then, for product development point of view, that provides a wealth of information for industries to develop their materials or their advanced materials that they have made using additive manufacturing. This is another example of how advanced measurement solutions is required for these advanced materials. Viewing this material using normal SEM parameters, it's not so easy to distinguish these dark regions. However, dropping the voltage down very low, now we can start to see these black spots. Don't know if you all can recall that we recently had many packaging issues when it comes to food. And one of the reasons can be this sort of degradation happening. And using this advanced equipment, we can now probe down to that nanometer level. And this then allows industry to correct or to do some of their, to have a look at some of their processes of where this to prevent this. If you have ever drank a Coca-Cola or a whatever soft drink before and you taste the metallic taste, usually it never happens. Sometimes it does. And of course, we need to know why. So these advanced measurement equipment really can illuminate or reveal things for us. Then moving on to the research sphere, of course, NAMISA also supports some key projects which we have identified, which we agree to be from an energy point of view. In this case, researching into solar cells, locally manufactured solar cells, to try and contribute to finding solutions for our energy crisis as well. This is a Perovskite solar cell, quite interesting material, very rapidly development within this field. It also cuts across a lot of materials characterization equipment. And this specific material, because of these accurate measurements and comparing different techniques and finding ways of improving the resistance to degradation, which is inherent for these sort of materials, it's possible then to make these materials locally, to produce them to be a solar cell with, for now, almost 12% conversion efficiency. This is an easily upscalable process to industrial levels. So NAMISA is involved in some projects from the start to try and always keep up to date with recent developments. We also have an X-ray diffraction, as I have mentioned, and this is one of the techniques that, even though it's been around for a very long time, it's still useful for these advanced materials where we can estimate how much of if it's crystalline, you can also get the amorphous fraction. But here we have a 24% mixture on a zero background holder, and from fitting the complete profile and doing this Rietveld refinement against standards, against with calibrated equipment, we got quite close. This is just a typical example showcasing how XRD can be a very good, insightful technique if we use it correctly. Then we also have another technique called X-ray reflectivity, XRR. This is one of those techniques that can give you a wealth of information for thin films and coatings, which is quite relevant for many industries. If your material is below a few hundred nanometers or so, where you can get your roughness, your density, or interfacial roughness. So microelectronics device performance can be monitored, or it can be extracted using this sort of technique. And I'll show you an example of it later on. Here is also surface structure of a copper foil that is used to manufacture graphene. Graphene is one of those 2D materials that has been identified to be industrially relevant, and South African, there is some activities in it. So NAMISA is already laying the framework for it, or laying the foundation for it. So this is a grazing incidence X-ray diffraction pattern of copper foils. If you do normal XRD, you will just see copper. However, because we want to view the surface, we use grazing incidence XRD, and now we can see the copper oxides. So we need to bear that in mind, that if we want to synthesize hydrogen, we need to stabilize this, and we can treat the surface with hydrogen, it is possible. So then we can get just the pure copper surface, basically. Electron backscatter diffraction, or EBSD, of the same copper foils confirms the EBSD of the presence of these copper oxides with some copper shining through. So this can be further improved or reduced, this oxide, using hydrogen treatment to get to this is an EBSD image of those crystals. It's a highly magnified image. It looks like sweets, but it's just grains. And these grains are all color-coded to show their orientation. These grain boundaries, the grain orientation, and the size, all of that influence the synthesis of graphene. So this technique is quite vital for industry to use to grow their graphene sheets. Hafnium oxide is another one of those thin films that has been recognized as a potential candidate and industrially relevant candidate to supplement or even replace the silicon-based microelectronic industries. So this is part of an international laboratory comparison that we're doing with the likes of NIST and PTB and those sort of NMIs in the world. So in a way, there are many ways to try and get this thin film thickness. However, we have been working on this EDS, which is quite a relatively accessible technique that has its limitations, but it can be used to extract the thickness of hafnium oxide. And we'll compare it against the internationally accepted XPS and XRR versions here in this slide. So here we can see, if you look, this is the reference thickness. It's quite thin, which is required nowadays for advanced microelectronics. XPS is the standard, which is these black cubes here. At higher or at slightly thicker thicknesses of thin film, the EDS and XPS can compare. However, the XRR is slightly dependent on the density. This graph just shows us that there is differences, and there is, even though you can measure the film thickness, comparing it, we need to be aware of the limitations of techniques as well. EDS here for very thin films, it can become quite inaccurate. However, XRR and XPS can still be highly comparable as well. So there are different ways for measuring different things. We just need to be aware of the limitations of each technique to ensure that we measure these materials correctly. Then this is probably the most important slide in my presentation. NAMISA, we are ultimately traceable, or we are part of the International Bureau for Physical Measurements, the BIPM, which is situated in France. So we are a founding member of this group, and we also have all of our activities in the surface analysis working group. Is quite important from an industrial point of view, in that it lays the work for standardization activities. So this is just to assist in identifying and establishing inter-laboratory work to improve the traceability to the SI units of spatially resolved chemical surface analysis at the micro and nanoscale. For example, the amount of silicon oxide as a thickness of SiO2 on silicon. This was important for the new kilogram project, which I showed in a previous slide on the silicon sphere. Equally important is the Versailles project on advanced materials and standards, the VAMAS. VAMAS supports world trade in products dependent on advanced materials technologies through international collaborative projects aimed at providing the technical basis for harmonized measurements, testing, specifications, standards. And these are the sort of working areas that are currently active under this group. These two groups basically at the end of the day allows us to compare our results here in South Africa, our measurement expertise in South Africa with the rest of the world, to ensure that we are comparable, to remove any barriers to technical trade, and it provides the technical basis. For example, VAMAS is quite important. ISO will not be where it is without the likes of VAMAS, which provides the materials or the pre-standardization technical work that has, it's just brilliant institutes, both of them really, that allows us to become comparable internationally. So both of these groups, NAMISA is on the steering committee for these groups, and we develop on behalf of South Africa and by request by South Africa's industry and research. If you want us to include intercomparison studies on here, please do contact us. We will then definitely ensure that it gets incorporated into this activities at this level of metrology. So in conclusion, we support the local advanced materials industry through materials characterization services and expertise. We also have strong membership to international standards bodies such as the BIPM, ISO, and VAMAS. We work closely with SANAS and SABS to ensure that we can contribute to standards development for South Africa's advanced materials industries. These standards are required for us to trade internationally, to sell our product, to ensure that our product meet international standards, so that we can, remove barriers to trade. Some of these measurements that is important is XPS, TOFSIMS, FIPSEM, EDS, EBSD, XRD, and XRR. All of these techniques are based at various institutes in South Africa. So these sort of equipment, or this is just example. It's not all of them, but it's just examples of what is required at the international level for standardization and for ensuring accurate measurements of advanced materials. We also have CT scanners, profilometry, TGA, thermogravimetric analysis, DSC and UV-Vis for optical, mechanical, and thermal stability properties. And with that, I would wish to thank you for your kind attention. And here's some contact details. You can contact me directly for any questions, or you can visit our website if you need any further information. I thank you.
Thank you, Dr. Clive Oliphant, for the presentation. I just want to remind the audience that we will have a Q&A session at the end of as the last item of the program. So please keep all your questions safe until we get to that item for all the speakers. So you can just take note of your questions as the speakers go along. When we get to that item, you'll be given an opportunity to ask questions, then the speakers will be able to respond. Our next presenter or the speaker from the program will be CSIR, Prof. Ray Suprikas. He will also be doing his presentation around different techniques for characterization and measurements, including device manufacturing and advanced materials. Over to you, Prof. Ray Suprikas.
Can you see my slide?
Yes.
Okay, so let's stop my video. So yes, I'm Suprikas Sinare from DSICSR Nanotechnology Innovation Center. It's part of the bigger center called Center for Nanostructure and Advanced Materials. So I'm here to give you a brief overview of the center and also, some of the characterization facility. We are setting up now nano micro device manufacturing facility. So first you will see how, as this is an innovation center, so how we are taking some of the, our research from the fundamental to commercialization up to licensing to industry. And that is quite compliment was one of our colleagues from TTI Nontombi presented, and she was one of the instrumental to set up that this center. So thanks to you, colleagues. Good. So I will give you a quick overview within the 15 minutes allocated to me. What is our objective as a center? How we are responding to different national imperatives and global trend. Then, as see the white paper of DSI, everything circular. So how we are responding to that, to our white paper. Then some of the enabling technology and as a center, what is our value proposition, what we are offering to stakeholder, and to industry. And also give you some RTI value chain, some of the research areas group. Then you will expose to you industry development and characterization facility. Then one slide dedicated for characterization facility. What is our purpose? And some of the areas we are focusing to grow, like nano micro manufacturing, encapsulation facility, and graphene is a big area because that is one of the identified strategic material in our white paper. And where we want to see our center in 2020-30, And as is a is an innovation center. So this is the audited report just we received from DSI, and we are quite good on full value chain. So last 4 or 5 years we are 2 to 3 license agreement we are giving. So last financial year we transfer 4 license to different companies to develop technology based on nano. Then we developed 3 joint technology with the industry. We incubated 3 SMMEs and we released them now. They are setting up the business. We generated close to 9 million direct income from private industry. We got close to 11 million generated from international fund. Then we developed 12 new technologies. We filed 1 patent, 3 international patent registered, students, articles. So you'll see we are actually covering the full value chain as a center. And at present, we have a close to 92 researchers and various aspects of nanotechnology at the center. So what is our strategic objective as a center? We are strategic objective to develop nano-enabled and advanced material solution to meet current and future needs of our partners. And partners, mainly we are focusing on industry and develop sustainable polymer composites or nanocomposites, nanostructure production processes, materials to support polymer, plastic, health, and chemical industries. So this is our strategic objective. And that I said, close to 100 researchers. We have a 3 research theme or 3 research areas, you can say, within the center. And one is the nanostructure synthesis and application development. We are synthesizing various kind of nanoparticles. And you can see if you come to the center, we have a scale-up facility, and we are producing some of the nanoparticles almost a ton per day. And because if you are serious about industry, they want to see that you are able to produce at that level. And again, we are going to a full value chain of our full value chain of the technology development. We are nanomaterials, then we are developing intermediates, then up to nano-enabled products. Then we have a high-performance polymer composite and sustainable plastics. Here we are developing different kind of nanoparticles, enhanced polymer composites, and some of the natural nanofiller also we are benefiting. But here we are not focusing on any kind of upstream. We are focusing on downstream, mostly compounding, conversion, product development, up to life cycle option of our product. Then finally, we are working on a delivery system, and delivery system is for development of delivery system and convert and transfer, particularly various kind of bio-based chemicals, bioactive biomaterials, and we are developing different kind of solution, including both pharmaceuticals and cosmetic industry. So, and growth area, we are setting up the supercritical encapsulation facility. So I'll let you know at the end some of the facility. So what is our national imperatives? As a center, we are first objective or to implement national nanotechnology research platform research agenda. Then secondly, also implement the white paper and how we are doing here. Then also another aspect is to respond to national development plan, and we are focusing on some skill and innovation of the youth. You can see how we are linking quite a number of research areas on 4IR technology. And of course, DTI master plan, and we are quite involved. Involved means 2 of our colleagues were part of that team to develop the plastic master plan for this country. We are also part of chemical cluster, but we actively involved on plastic master plan. And of course, we are also responding to 14th industrial revolution, using nanotechnology by combining physical, digital, and biological. We are developing different kind of materials for a need for advanced manufacturing. And I will show you some of them just now. And again, if you go to our white paper talking about the circular economic thinking, we try to minimize the waste of materials. So we are developing different kind of, and we are focusing mainly now on materials efficiency, but slowly we are moving to carbon footprint mitigation as well. But here, how we are doing by developing different kind of nanocatalysis, waste to chemical conversion, and 3D printing is a quite big area now in our center. We are trying to use, carbon dioxide feedstock to chemicals using different nanocatalysis. Now we are able to convert carbon dioxide to methanol. We have a very nice now reactor. If you want to see, come and see, but not that level. A few milliliter we are able to convert now, but we are thinking to scale up that one. Then we are focusing on various kind of packaging design using nanotechnology to minimize the waste. Similarly, recycling, I think you saw, is a huge media coverage, how we are using some of the high temperature nanochemistry to convert plastic and mixed with bitumen for road is a huge area. We are actively involved in that area. Is funded by some of the companies and DSI and some of the other partners. Then also we are trying to use some renewable raw materials and using nanotechnology to convert that raw materials to different kind of advanced chemicals and materials. And of course, enable technology. We are focusing on advanced nanomaterials and digital transformation. So left side is different kind of capabilities and right side is different kind of response or areas we are application areas. So nanomicro manufacturing, that is part of our DSI infrastructure roadmap. We are now spoke and hub model. So we have one spoke and we are on behalf of DSI, we are also coordinating nationally that one. And virtual synthesis, you can come to see that we are some of the synthesis, we in a lab, we don't go everything happening virtually. Nanomaterial synthesis and also multi-scale modeling, we are now using the data science and to get all information of the materials before go and synthesize. And of course, using machine learning for reaction kinetics. So we are closely working with our high performance computing center at Cape Town and with our modeling department in CSIR here in Pretoria. And focus area is nanocomposites, for advanced materials, advanced metals. We are working with manufacturing cluster very closely. And also a different kind of drug developing in collaboration with our health cluster within the CSIR and energy materials. Also, we are working with energy center at the CSIR and other partners in the whole country. And of course, biomaterials. So here you can see how we are using nanotechnology and moving towards advanced manufacturing through the development of nanostructure materials. What is our offering? To stakeholders, and stakeholders, both government and also different kind of industry. So we integrate our knowledge of the market and unique set of capabilities. We have a dedicated business development team within the center and cluster. They are helping on market information, unique and set of capabilities, including skilled personnel with knowledge in advanced materials, lab scale R&D facility, characterization, and pilot scale facility to offer holistic technology solution to the chemical industry. And you can see in the second slide I show you how we are, our KPI, we are actually responding full value chain from the publication to technology development to scale up to transfer the technology to the industry. So we have you will get full access to skilled personnel and technology, and on advanced material synthesis, modification, characterization, application development, because now advanced materials means advanced nanomaterials. All are using nanotechnology and nanoscience for advanced material synthesis for advanced manufacturing application. Then access to world-class lab and pilot facility. We are very fortunate, and that I said that Nontombi was one of the instrumental to set up the facility. So we are very fortunate. We have a world-class characterization facility. And second stage, 2013, 2015, through the help of DSI and some of the industry, we set up very good pilot scale facility. And to access to, to the network and knowledge of market, you will get full knowledge of market, because we don't do research just sake of research, because for this reason you can see we have a technology transfer is quite prominent, and also technology development with the collaboration of the industry. And of course, impactful solution. We are trying to give sustainable and state of the art technology solution, which result in growth of industry. And that I say that we are integrating all aspects of science, business to make impact. So this is our value chain that I said at the beginning. We are starting from TRL 1 to 4. TRL means technology readiness level, up to we are going to TRL 9. And you can see here we are focusing more fundamental research, but fundamental research based on information available from the market. So more and more purpose-driven and industry-driven research, or sometimes some of the cutting-edge research that we are thinking that this will come in 5 to 10 years' time. And as I said, we are using various kind of modeling tool, 4IR aspect, and trying to, converting that molecules to materials in computer before we go to a lab, and catalyst design, synthesis of new generation materials for sensing application. And these are the research group. And this is the facility I will show you in one slide. We have a nanomaterials industrial developing facility. We can synthesize a ton of nanostructure every day. We have a now formulation of composite or nanocomposite. We can have a 300 to 400 kilograms per hour. And of course, testing facility. We are setting up the nano micro manufacturing facilities almost in a completion stage by end of this calendar year, and focus on lab on chip gas sensing using various kind of deposition technique. Then supercritical encapsulation facility, both mostly focusing on nano encapsulation facility. And this is, I have one picture what is going to see when it will be finished, and we are expecting by end of December we'll have it. And this is the partnership between DSI and CSIR through high-end infrastructure grant. And we are very fortunate now. We set up a joint venture between us and Coca at Port Elizabeth, that we set up now hemp fiber processing facility. That is also now part of my portfolio. When you are successful, CSR will give you more and more job. So we are now in the last stage. So that is a unique hemp processing facility and product development. We are in a completion stage. And you can say we are then materials characterization testing and analytical facility, giving the support from the fundamental research to scale up and transfer to the technology. So this is the way we are working at the center. And this is the sum of the facility that we said we are doing the lab scale facility. This is the scale, infra that I was saying, the nano encapsulation facility. You will see much bigger in the next slide. This is our polymer scale up facility. This is nano structure scale up facility. This is hemp processing facility. Now we set up jointly with us and Coca, and we are calling that is natural fiber hub. If you put natural fiber hub, you will see the website now there. And we have a characterization facility. I have a 2 slide. I will show you on characterization facility. And here, different kind of industry facing facility that we are talking about. And characterization facility, this is 100% funded by DSI. and focus is a multi-user facility and almost minimum cost, just a couple of hundred of rand, just stop the misuse. Otherwise, as is fully funded by DSI, is mostly using by academic and industry. Sometimes industry quite extensively they use the facility, but industry charge is different than academic. So facility, conduct, but also giving support to us as well. We have a very good 7-member team in the field. Their experience on different kind of different aspect of nanotechnology. Now we are building the textile, automotive, and leather and footwear industry. That is part of the DTI program, and again, this is brought to the center, because again, when you are successful, CSR give you more. So we are now working closely with DTI on this aspect to expand that capabilities. And it provides technical support to researcher to SA to achieve their objectives and technical deliverable. And technician research facility provide one-on-one equipment training when there is a need. And one of the best equipped scientific facility in South Africa. And also there is another component that I said, testing facility, that is the industry testing facility as well. And so we have a various, almost all kind of techniques, and some of the complementary what Clive presented. We work closely with NIMISA with number of techniques, particularly surface characterization. We use them a lot because we don't want to have that facility us, because that is within the campus. So yes, some of the area that I said, nanomicro facility, I will have one slide, I will show you. Then we are very proud that we developed a new kind of method to synthesize graphene from our graphite from our mines, and a couple of company now in the pipeline. Now we actually scaling up the facility, but just to be able to synthesize 2 kilograms. Now we are scaling up to 5 to 10 kilograms per batch. And also we are supercritical. You will see by end of this year. So we are hoping that will be opened by Minister of DSI sometimes next year, February, March. This is a facility, and this is a very neat facility because number of SMME, they are encapsulating a number of ingredients in Germany. We don't have any facility in Africa, so that will support significantly to the SMME, and SMME directly wrote to DSI that we should set up this facility at the CSIR to get the support. So it will be 100 kg per day and 100 kg of encapsulation of like probiotic. You can produce hundreds of kilograms of product. Then this is the nano micro manufacturing facility that we are, that I said is a part of the DSI infrastructure roadmap. And we are focusing on, low cost diagnostic device platform, and it got a 3 kind of legs, to develop the detection technology, biomolecular, sorry for spelling mistake, then device technology and point of care system. And this is our full value chain. And you can see that I said at the beginning, we working with health cluster, our chemical cluster, and also manufacturing cluster. So we are, is a joint effort to work together to develop this kind of product. And the CSI developed previously during COVID that ventilation is part of that kind of effort we are doing here as well. So we are hoping that it will be done by end of this year, and we start supporting SMME and others from the next year. So finally, this is my final slide. So where we want to go in 2030, and is a big vision for us. that we are enabling global competitive industry reputable innovation center, and we are focused on digitization, globalization, and sustainable to grow South African economy and become a global leadership in AI-enabled nanomaterials development is quite part and parcel of our business. And this is, we started this, this kind of vision 2019, and 2030, we want to have a, go-to product innovation center. We are very fortunate. We have almost 4 to 5 industry every year, and quite number, because we have to increase the number of our capabilities, means our workforce, because then we can host more companies to support. And some of the platform fully funded by industry. Now you see that our center budget is around 130 million, and we get support around 45 million from DSI and CSIR, and remaining we generate from industry internationally, a number of projects going on. And fully integration AI enabled new materials development facility, intelligent materials for apply for various industry, and full-scale establishment of nano micro manufacturing facility to support our SMMEs and our own capabilities, because COVID actually opened up eyes that we have to be sustainable. We cannot depend too much on outside. Then also global center of excellence we are looking for, that material synthetic digital chemistry using nanoscience, open lab, industry partner, like we are quite R&D partner of SAPI Netherlands and SAPI South Africa, a lot of work coming from them. Then also reality training to develop different kind of synthesis method, and of course international industry partner. And you can see we generated 11 million last financial year from different international industry. So it's quite good as a center coming foreign currency to the country. So I will stop here. Thank you again for this opportunity. And if any question, I'll be happy to answer.
Thank you very much, Prof. Ray. The question and answer session will be at the end of the program, but there is also a Q&A button there at the top of the screen. If you like to type your questions, you can do that, and maybe the speakers can also try and respond, but we'll also touch base on that when we do the question and answers session. Our next speaker would be MinTech by Prof. Lucky Shikwivilu. He will also be covering the topic of different techniques for characterization and measurements, including device manufacturing and advanced materials. Over to you, Prof. Lucky. Prof. Lucky. Faith, is Prof. Lucky on the call?
Yes, Falani was. Let me just quickly call him as well.
Okay, thanks. Maybe while we're waiting for Faith to contact Prof. Lucky, Dr. Hannes, are you ready for your presentation? So that we
Yes.
don't waste time, maybe we can move to the next topic, which is the overview of nanotechnologies in standards in South Africa, labeling requirements on nanomaterials containing products, which will be done by Dr. Hannes Foster. Dr. Hannes, if you are ready, you can go ahead with the presentation so that we don't waste time. Then we will take Prof. Lucky after you. Over to you, Dr. Hannes.
Thank you. Can you see my screen?
Yes, Dr. Hannes.
Thank you for the time, and yeah, it's a privilege to be able to present. I'm Hannes Foster, chairperson of SABC TC 229 and Nanotechnologies. So I'm going to just give a brief overview, historic overview of the committee. Then also define objectives of SABC TC 229, specifically as it relates to sustainable nanotechnology, look at the membership, the working group, lists of published standards, then also look at the South African technical specification guidance on voluntary labeling for consumer products containing manufactured nano objects, then what is the South African approach and the revised European Commission definition of the term nanomaterial, and then context. So just as an historic overview, the first call to establish a national technical committee by the SABS was done in February 16, 2007. This was requested by DST. The first meeting was held that year at the SBS. Dr. JJ Molopisi from DST at that stage and Mr. Abdul Manaka from SABS were like the founding members. In November of that year, we changed our participation at ISO from an O to a P member, from observer to a participant member. And then also we changed the name in 2008 from SA Stanza TC 5140.49 to SABS TC 229 Nanotechnologies to mirror the ISO TC numbering system. And since 2008, this committee has been an active participant at the ISO TC 229 meetings. Then maybe just an overview from our strategic business plan that we've got certain defined objectives that we would work closely with ISO TC 229 to develop robust standards and other deliverables relevant to nanotechnology that will support the sustainable, responsible development and global dissemination of emerging technologies, facilitate global trade in nanotechnologies, nanotechnology products, and nanotechnology-enabled systems and products, and always taking into account that we don't have any problems with technical barriers to trade. Support improvement in quality, safety, security, consumer and environmental protection, together with a rational use of natural resources in the context of nanotechnology. Promote good practice in the production, use, disposal of nanomaterials, nanotechnology products, and nanotechnology-enabled systems and products. You've heard some of our members today already, but we've got quite a broad membership. We've got industry association, the chemical and allied industry, the CTFA, we've got the University of UNISA, Northwest, University of Western Cape, University of KZN, and Rhodes University, I think, is in the process of joining us. Then government departments, We've got DSI, DOLE, DMRE being members of our committee. Science Council, CSR, Mintech, Itemba Labs. Then private companies, we've got L'Oreal, Prime Product Manufacturing, NAB Consult, TD Coating Center, and Top Solutions. And then technical infrastructure, we've got the NRCS, NMISA, SABS as our hosting organization, NIOH and NHLS. Then we've got 5 working groups that we're mirroring at the ISO level. The first one, terminology and nomenclature. Second one, measurement and characterization. Third one, health, safety, environment. And in this specific working group, there's a lot of activity also to look at the safety of nanomaterials, disposal, the life cycle, the biodurability. We've got also working group 4, material characterization, and working group 5, products and applications. Our approach has been to firstly look at, standards covering health and safety. And then also we looked at the technical specification guidance on voluntary labeling for consumer products containing manufactured nano objects. I will discuss that a bit later. We're also quite proud of this standard. It was locally developed by Professor Mary Galubian and also published at ISO. It's a technical report on use and application of acellular in vitro tests and methodologies to assess nanomaterial biodurability. And then our approach has also been to look at vocabulary standards so that we're able to inform the local researchers of what's happening in the world of nano at an ISO level. What's the core terms, what's the nano objects, what's carbon nano objects, nanostructured materials, nanobio interface, nano object characterization, diagnostics, therapeutics for healthcare, and nanomanufacturing processes. This would be able to disseminate into the South African industry, and I think part of today's webinar is also to expose some of the attendees to the standards that are being hosted by the SABS so that they can alert themselves of what's happening in the vocabulary space. This technical specification, the guidance on voluntary labeling for consumer products containing manufactured nano objects, just as a bit of a background to it, it was developed by CEN, the European Nano Committee, and eventually taken to the ISO level. And yeah, the decision was made at ISO that it must be voluntary labels for consumer goods. And it's not applicable to products that contain naturally occurring nano objects. So that's just a brief overview of the scope. So in terms of this, the identification description of manufactured nano objects, manufacturers may voluntarily disclose the presence of manufactured nano objects in consumer products, provided that such labeling does not conflict with any applicable legal requirements. For such voluntary labeling, information that the PCMNOs should be provided either as part of the ingredient list on the label by placing the term nano or nanoscale before or after the commonly used name of the manufactured nano object, unless the name already contains something like carbon nanotubes, or by placing the phrase contains manufactured nano objects. Just a comment, where it's possible, it's preferred that the first above list option be used. So then we looked at, what's the South African approach? One of our sister technical committees is TC217 Cosmetics. And in this committee, the CTFA is a self-regulating industry body that follows the EU directive for cosmetics. So Europe have taken a different approach. And I think that the comment was globally there's ambiguity on the definition of labeling requirements of ISO versus the EU. And there's different definitions on limits and requirements. ISO standards leave the interpretation of nanoparticles up to the manufacturer. And this is further complicated by the lack of clarity surrounding percentage of particle content soluble, which would then not be nanoparticles versus insoluble materials. So TC217 has taken an approach of following the EU directive. Other TCs have still to determine the applicability of this technical specification on voluntary labeling. And they would further engage with our committee also in terms of that. Then interesting, in October 2011, just to see what Europe was doing, is their definition of a nanomaterial was a natural, incidental, or manufactured material containing particles in an unbound state or as an aggregate or as an agglomerate, or where for 50% or more of the particles in the number size distribution and one or more external dimensions is in the size range 1 to 100 nanometers. And quite recently, there's been an update by the European Commission. The revised European Commission definition of the term nanomaterial was adopted on June 10 of this year. The full text can be found on this link. The fundamental principle may be that a nanomaterial is defined as a material where at least 50% of materials have at least one dimension, less than 100 nanometer was kept. The main changes of the revision are it explicitly covers only solid materials. Constituent particles must be identifiable, and criteria to demonstrate the material is not a nanomaterial was set. A volume-specific surface area of less than 6 square meters to cubed centimeter, or 2 orthogonal dimensions bigger than 100 micrometers. Specific mention of graphene or carbon nanotubes were removed and replaced by a generic inclusion of nanorods or nanofibers or nanoplates. As with the first definition, this Commission recommendation does not have immediate legal effect. The idea is that the definition is applied with the various pieces of legislation covering nanomaterials as revised. And that's the European Joint Research Commission is working on a guidance document on the revised emission. I think if you look at this approach, I think Europe has taken an approach of trying to have specific ranges and definitions of when you must label it, and parameters for industry. In South Africa, we still have to decide what our approach will be. Certain committees, like the Cosmetic Committee, is following the EU directive. There might be other approaches in other countries that South Africa might follow. Just the contacts for our committee. The committee administrator is Winnie Mshlangu, and the standards writer is Faith Sanyangara. And I just want to say thank you for your attention. A special word of thanks for the committee members for their active participation. Winnie Mshlangu and Faith for their hard work for TC229, and Veronica Malapana and Follen Muruvelu and their teams at the SABS. Thank you so much.
Thank you, Dr. Hannes, the SABS TC229 chairperson. We will go back to the previous item, which will be covered by Prof. Lucky Shikwivilu on different techniques for characterization and measurements, including devices, manufacturing, and advanced material. We will hand over to Lucky before we move on to the second last item on the program, which will be the standard presentation by Dr. Sadvi Bison. Over to you, Prof. Lucky.
Thank you very much. Can everybody see my presentation?
Yes.
Much appreciated. All right, so this is the title that I took from what was sent to me. I do apologize, not everything looks easy to read. But my name is Lucky Shikwivilu and I'm from Mintech. So we're going to share a few techniques that we have at Mintech. I've consulted with some of my colleagues to ensure that I do not come here and repeat most of the stuff that they might have talked about. So I've really put a short presentation. Hopefully you enjoyed. All right, I thought the best way really to kickstart this will be to give a perspective in terms of what I plan to share with you. And the reality really is we want to sort of review the analytical methods that are available at Mintech, or at least at our disposal, so that we can understand the properties of nanoparticles in respect to your composition, morphology, size, charge, physical state, and stability. This is particularly important because then it could be used to propose a number of standardized protocols. Now, this for me is a buzzword, and not simply because we want to characterize material the same way that others do, but rather because there are so many things that could go wrong if characterization is not done right. And it puts limitations to how much we can do and how far we can do with the science that we do. And I'm going to try and put some context to that. I want to take you back to about 1970 when Professor Aiji Osawa of Japan, I think he's from Kyoto University, he did some experiment and published a very useful publication that you can see on your left, production and characterization of supersonic carbon cluster beams. He characterized everything and assigned almost all the peaks. What you see highlighted in red is the C60, which he, for some reasons, chose not to say much about it. Move from that forward, a few years later, in about 1996, a group of researchers were credited with the discovery of the fullerenes, something he should have done back then. But because he had missed that peak that's highlighted in red, that simply meant he missed a Nobel Prize for it. Now, that is disheartening, but that's what happens when characterization is not done effectively and efficiently, and that's the essence of what I'm trying to say. I'll give you a second example. We're all familiar with Prof. Ijima, also from Japan, credited for the discovery of carbon nanotubes, perhaps known by many as the father of nanotechnology because he brought it to life. Of course, that's notwithstanding the great researchers such as your Richard Feynman. But he brought it to life, and that was such a big thing. But if you go back in time, you will see there was a patent, a US patent for that matter, that pretty much covered everything. So these guys should have been credited with this, but because of the way the characterization was done, that became another limitation in terms of how far they could go with it. So characterization is by every measure particularly important if we are to derive meaningful information for the kind of research that we do. And missing it by a little bit could cost you dearly. And at the same time, it could be a start of somebody else to thrive based on what you might have put forward. So that's important, I think, for us to be aware of that. Because even in modern day, with all the kinds of technologies that we have, we still miss out on important information that could easily lead us to leading the world in some ways. So I thought let's rather look at some of the different application areas. There are many application areas for nanotechnology, and I think most of us are familiar with this already. Some of them covered by the previous speakers. So they range from energy, whether be it in the form of storage, defense and security, metallurgy and materials, or advanced materials, if you will, electronic devices, and you name it. Agriculture, this could come in the form of food security. So there's so many applications, health, biomedical, drug delivery. So all these are possible areas. But I thought to kind of give perspective to what we do at MinTech, we will try and restrict it to the areas that are on the far right, which will be your materials. The focus on the material for us is mostly on the mineral-based type of materials, not because we're trying to be fancy, but that's simply because we have access to minerals in the country, and part of what we really intend to do is the beneficiation as well as the value addition to these minerals, so we could use them to build the future that we want, really. The biomedical or health, if you will, electronic devices, water, Food security, I've already referred to that. So these are some of the areas that I might mention as I tell you more about the few things that we are able to do at Mintech. So I thought let's perhaps start with the surface techniques that we have. And I've decided to put them more in pictorial form, but the pictures will tend to depict more the instrument than the output that you get out of it. Nonetheless, I do, sort of expect that everybody will still be fine with it. High resolution TM and high resolution SCM, those are common equipment for nanotechnology in particular, because you get all the information about the morphology, the microstructure of your particles, which is absolutely necessary in order for us to visualize particles in their respective ways. But it also helps us to start looking at the size of this particle and the size distribution. The systems that are attached to them may not be as perfect as they should be. So the information that you get is not always as perfect as it could be. For example, if you're looking at the particle size that you get from TEM, it's a very close approximation of the actual size of the particle, but often at time not exactly the same as it is, but it gives us a sense of how we move forward. Some of you may be upset by what I'm saying, but that's a fact. On the other side, you have systems such as differential, what do they call it? DLS. For some reasons, I forgot what it stands for, but I'll tell you just in a moment. I'm sure I'll remember that. Dynamic light scattering, I think that's what it stands for. If you look at it, two things that you can do. You can look into sizing up your materials. That's one part. You want to get a sense of the particle size, to some degree, particle size distribution in solution. So you're talking about the colloids that are suspended in a solution. That's a very good system, but it's got its own limitations, and those limitations would include things such as anything that's optically based. In other words, anything that's based on the light. The limitations that you often have to deal with would include things such as depending on the orientation of the particles, you may not get all the information. So what it means is if you have something that looks somewhat like a rod and you're trying to measure out the size, depending on how the light comes through, if it comes through from the elongated side, you might have the particle size that looks somewhat far much larger than it should otherwise be. On the other side, it may also depend on the behavior of the material in a medium. So some materials, when you put them in a medium, they swell up. So the size that you measure out using this could be something else, and it could be far from the reality. So those are some of the things that one has to be aware of as you make use of this. But other than that, you get information such as your particle stability or the colloidal stability, as it were, which tells you exactly how stable your particles are in a particular medium, which is particularly important because you're looking at your ground wind motion and things like that. I won't go too deep with everything, but those are some of the things that we kind of look at, and it's important to collect information about where we're going with everything. You have XPS that will give you a very sensitive information about your nanoparticles. That's particularly useful depending on what you use it for, but relationship between things such as your binding energy and the oxidation states, such information can be obtained from here, and that gives you a whole lot of information that you could use depending on what you're really trying to achieve. On the other side, some call it a blind man in a form of a technique, the AFM, that helps you to get the topography of the material. And so that's particularly important to understand, the topography, as I said, of the material in a way different from TM and SCM. So you can determine the surface roughness, and that really helps you to understand really the surface of your material and the potential or the ability for the particle to react with other species as well. So that's important to have that. And of course, I've just chosen just a few so we could make sense with where we're going. More characterization facilities. FTIR, perhaps, more commonly used, research equipment. But on the right to it, you're looking at something that looks somewhat like a spaceship. That, by every measure, is just a drift cell. So this allows you to do certain measurements that you otherwise would not be able to do with simply just FTIR. It's not just about the functional groups that you may be looking at to identify the species that you have. But in this case, you may be looking at more things than that. And I think to give you context as to some of the things that you may be able to do is, of course, where you have drifts, I think just kind of imagine when you're trying to look at certain materials, maybe let's say for this case, indium nitride as nanowires, and you're trying to detect as a sensor device, say some carbon monoxide or something like that. So to determine the interaction between your material and the gas molecules, whether these be it in the form of physisorption, or it could be in the form of chemisorption, you can determine all that using drifts. Which is nothing but diffuse reflectance infrared Fourier transform spectroscopy. So that helps you really to get more sensitive information than you would otherwise get from your typical FTIR. So that's important to have that. It's particularly important if you're looking at materials such as catalysts, because adsorption, desorption studies then become ever so important in order to move forward. And I thought let's rather even also put the surface area. Nanotechnology for the longest time has been assimilated with the growth of the surface area as a result of making these particles as small as they can possibly be. But one of the things that you then need to look into, depending on your application, is to understand the surface area of the material, and that can be also looked into in respect to the volume. So that's important to understand. But in doing that, there's so much information you can get. Information that goes to understanding the pore volume, the pore size, including the pore shape. So many isotherms that we work with that sort of shed lights about what kind of pore shape do you have, because that in many ways will talk to the properties that really affect the porosity of the material. So that's important to have that. And this is just one of the characteristic equipment. We call it a TriStar. It allows you to do that. So you can do all kinds of measurements to obtain the kind of information you need. There are many others as well. I did not limit it to simply what we have at Mintech. But one of the things that, of course, we make use of will be your ICP, which is inductively coupled plasma mass spectroscopy, which is on the far left of your screen, in respect, of course, to my view to the screen. The one good thing about it is that we make use of materials such as your gold nanoparticles for the development of health-related products. This could be in the form of diagnostic tests, mostly the rapid diagnostic tests, which could take any other platform, whether these be it any simple platform or even more complex. But the reality is, half the time when you conjugate gold nanoparticles, we all want to believe that the size is everything. But what we don't often talk about is the importance of having some ionic species in the system, and what exactly do they do, and about how much of those can you have. So you do speciation with this equipment, you get all kinds of information to understand exactly what stabilizes your system beyond what we assume would be the reality about it. So that's important for everyone to kind of have that information. You also have what we call OCT, which is the optical coherence tomography. And the one big thing about it is that we have a project, for example, where we're trying to inoculate an animal in the form of a mouse. and you inoculate, say, for example, with gold nanoparticles, and you're trying to track down the evolution of gold nanoparticles, whether they somehow coalesce and form far much larger particles, depending on the medium they're exposed to in vivo. So that's important to somehow track that down. So it's an imaging technology, but it gives you a very useful information. However, the limitation of not always being able to measure out the particle size to the greatest possible precision would mean that you have limitations. But we've partnered with Zululand University, and what we've done with them is to really look at mathematical approaches, which is nothing but really your mathematical approaches to determine the exact size as exact as possible. Because when you start getting the stacking of some of these particles, it's very difficult to determine what the real size is. And also the effects of them aggregating to form much larger particles and thereby affecting the performance of your material. So that's important to have that, and that's basically one of the areas where we use it for. On the far right, you have something called XFs. We normally use that with a technique called ZANES, and this thanks to our collaborators in the US and in Europe, because that helps us really to determine things that are otherwise very difficult to determine using a simple technology. And to sort of give you a sense of what we mean by that, if you think about it, if you have something like, say, indium tin oxide, which is like a transparent, a thin layer type of a thing, but it must have some transparency, so you can use it in technologies such as your flat screens, flat panels, if you will. It's a very useful material, but it's very expensive. And to really substitute that, you could use other materials as well. One such materials that we've used is alumina that's anchored on aluminium that's anchored on zinc oxide, for example, to get the same kind of properties. But then the challenge becomes, how much of this alumina can you add to zinc nanoparticles, and how much capacity does zinc oxide take from this alumina? And when it does so, where exactly does it sit? Does it sit on the surface? In other words, if you imagine you have a particle of zinc oxide as a spherical one, does it sit on the outside as little dots that sit on that and well distributed, around the particle? And if so, about how many of them can you put as particles, depending on the size? But on the other side, sometimes things don't work the way you expect them. You end up with a doping system where the particles, in fact, actually go into, either they go into the lattice or into the interstices. And if they're trapped somewhere in the interstices, the question is about how much a specific particle size can take of this aluminium into the framework. Because then if you can work that out, then you kind of know exactly about how much you need to put in. It talks to more efficiency and all of that. So these are kind of techniques that we use to solve issues with. But the challenge with them is that the data processing can be a treacherous process because it takes a long time and you require a lot of calculations out of that. But that's what science is about. So I thought let's also kind of quickly move into the manufacturing facilities, so we can talk about infrastructure that's in place also for manufacturing, because as my previous colleagues have already addressed this, we're not just doing research for the fun of it and for the generation of new knowledge, but it's also about how we can take some of this knowledge and package it as products and technologies that can be used to improve the quality of life for everyone in the country and beyond. So to do that, you've got to somehow be able to have a strategy of how you approach it. I must sort of qualify it at this point that if you look at various manufacturing systems that we have, they talk to each other in one way or another. For example, you may be looking at application in health. You need the materials, so you cannot scale up the production of the health-related products if you can't scale up the production of the material itself. And do you just simply scale up for the application, or you scale up as a product by itself, such that you could also sell it to anybody who needs it for other applications. The latter is true for us, and that's how we look at it. And so what you're seeing on your screen really is us making efforts to scale up the production of nanoparticles, depending on which ones they are. The one on the far left is gold nanoparticles, but we really scale up almost all the materials that we make. And we make them available as products for others to use, either for research or for development of products. That's important. In the middle, you're looking at the infrastructure, and this is not really like a characterization facility per se, but it's rather an equipment that we use to scale up the production of formulations. This could be in the form of polymer formulations that can be used for different things. It can be used when you're looking into developing membranes for the detection techniques or diagnostic techniques for that matter, but also polymer materials that can be used for other purposes as well. So you need to be able to scale that up. And on the far right is when you go a lot more higher in terms of the quantities that you're producing. And we are in the process now of developing, or rather constructing a new building for manufacturing of nanoparticles. And the reason for that is simply because unless we do that, we miss an opportunity to ensure that we comply. In the health side, you need to comply by being certified, even as a producer of nanoparticles, to ensure that that ties in with the manufacturing expectations from the health products. So that's important that everything is created and generated from a facility that's also accredited, so you generate the right quality to move forward. The health products, I've already referred to them. This is one of the state-of-the-art infrastructure for the production of some of these kits. Right at the bottom of each slide from the previous one, just a little glimpse at it. These are the typical products. We have many of them, but I just gave a few of them so you have a sense of exactly what are we producing or using the infrastructure to produce. So this is the infrastructure where we produce lateral flow based type of assays for diagnostics of different diseases. And the diseases are often informed by the priorities from the Department of Health, from MRC, who also play an advisory role to our existence and our structure. So that's important to have that. And we've used this to really develop products, as you can see from the bottom, that range from your HIV, malaria, TB, you name them, but also, you know, of late, COVID-19. So we've produced both the antigen-based as well as the antibody-based type of products. And we are already looking into going for a tender, not just with COVID, but also with your HIV. And hopefully we will be entering the market very soon with our products. I'll give you more information later as to some of the steps that we've had to go through to be ready so that we can start adding value to, you know, growing our economy. On the other side, which still in many ways talks to health, is the health that I referred to in the previous one is mostly the qualitative kind of approach to diagnostics. But on the other side, you may also be looking at the quantitative, and a glucose sensor, for example, will be a typical example where you're not just interested in knowing that a person has glucose or not, because all of us do have it. But it's a question of about how much of it do you have, because then that talks to whether or not you have a problem. You have a problem of having too little of it or too much of it. Either way, you could have issues with that. And we do know that having too much of it is potentially the biggest issues that we have, which is lifestyle based, and that will be your type 2. So we've got a screen printer. We generate different types of electrodes. They range from basic electrodes that you can use for research. They go to very specific electrodes that you can use for identification of very specific diseases. We put them on different substrates. They range from plastic to glass to even ceramics. So depending on what you want to use them for, you have all that information. Once we have done that, we try and validate them so they work the way we expect them to. And on the far left, right at the bottom, is the reader that kind of gives you information about whether or not you have issues. So it will give you a digital data that tells you whether you need to be worried, to be stressed, or just to be happy. From the water side, we have set up a manufacturing facility. All of this really is to develop this little straw-like, which are what we call capillaries, which we use to fabricate membranes. And right at the bottom right, you can see a 1.2 membrane module that you can sort of use in any kind of plant, whether it's be it a mining plant, where you want to reuse your water or retreat this, or it's energy generation like your ESCOM, your CESOL, a whole lot of industries that are sort of dependent on whether or not we can make some of these locally. And we are at a point where we're just finalizing this, and we're hoping to enter the market pretty soon on the production of this. We're not limited to the capillaries alone. We also do the flat sheets, which you will see on the picture that I'm sort of showing, the rolled up one. And of course, we also do your resins or adsorbents, which we normally put in filters. This could be point of use type of filters. So you can have these as materials that you replace every now and then and make use of your point of use filters to treat water at your household, so you retain the right level of quality of your water. So that's important to have that. All of this is not possible unless you also comply with the expectations. The expectations is that you need to have specific laboratories that are certified, whether you obtain what we call ISO. In some instances, we look for SABS approval, but all of these have to be in place if you are to play in the space. Similarly, so when you're looking at medical devices, you also have to be approved by SAPRA to have the manufacturing license. And on the right of the screen, that's basically what you guys are looking at, the license to manufacture some of these products. That tells you that you are already, if you have this in place, you're playing in the space of the highest possible quality. When it comes to health, there's nothing less that is expected. It has to be the best or not at all. You can't have it any other way. So that's important to have a lab that can do that. In conclusion, I just want to simply say the material characterization is of utmost importance in research, simply because it helps the reader to build a more vivid mental picture about whatever the material they have and what it can do. So that's important to have that. But on another level, it also helps whoever that works with material to understand the physical, chemical, mechanical, and microstructural properties of the material. And we can list a whole lot of them beyond what I put up here. But last but not least, it could also form the basis for understanding the composition of device materials and its potential for an adverse biological or physical effect. So our interest is not so much just the material, but is also understanding that once it's bound on a system, how does it perform? What could inhibit its optimum performance? What do we need to do to ensure that we get the most out of it? So that's important in that respect. And with all that, I thank you, and I do hope that it gives you perspective about some of the things that we do and how we solve issues. Thank you so much.
Thank you, Lucky, for the presentation. We are behind on time because we're supposed to be done by now and take a break until 1 o'clock according to the program, and start with the next session at 1. And it's now 4 minutes past 11. And we still have one more presentation before question and answer session. So the next speaker will be Dr. Sadvi Bisun, Standard Executive, SABS. He will be doing his presentation on the role of standards in South Africa. Over to you, Dr. Sadvi Bisun.
Thank you, Fallen, and good morning once again to all the colleagues. Program Director, I must apologize for being late. I was supposed to open up this meeting with the introductory presentation about the role of standards in South Africa. But I think, and I stand between you and some rest break as well, which is well deserved. So I'll try and be very brief. I'm just going to put my camera off so we'll be able to make sure that we have a seamless presentation today, and then put my presentation on presentation mode. Chair, can you just confirm that you can see my presentation?
Yes, Sadvi.
Great, perfect. So the title of my presentation is the role of standards in South Africa. And just to provide some context, I think it's quite appropriate to provide you with the legislative framework of SQUAM institutions in South Africa, which is basically the quality infrastructure institutions, our mandate and how we relate with each other. So SABS was founded in 1945, so we are 77 years young, I would put it. Because there's not a day that goes by where we are always learning new things, developing new standards, conformity assessments, services, etc., based on the highly dynamic ecosystem that we operate in, both nationally, regionally, and a global basis as well. So our mandate, as per the legislation, as mandated by the Act, is to develop, promote, and maintain South African national standards, referred to as SANS, the acronym. We're also responsible to promote quality with respect to commodities, products, and services for domestic and export markets. And last but not least, provide conformity assessment services. And these are in the form of certification, testing, inspection, and verification services. There's one regulatory body, which is the NRCS, National Regulatory Services for Compulsory Services, or standards rather. They're responsible for the administration of compulsory specifications, and most of their compulsory specifications, which are part of regulations, are referenced to South African national standards. So we work very closely with government entities, the NRCS, to manage their regulatory environment. SANS, South African National Accreditation System. This entity is very important to make sure that bodies like certification bodies, testing, inspection, verification bodies have the infrastructure and necessary resources to provide these services aligned to international best practice and international standards. And last but not least, the MISA, who is part and parcel of the panelists today and presented. They are responsible, as per their mandate, for calibration through measurement, accuracy, and measurement traceability. So these four institutions play a very important role in ensuring that we provide quality assurance, standards and quality assurance, and provide for an easy functioning of the economy as well. So just as a graphical representation, we develop South African national standards. These standards are copyright protected, and they all reside in terms of copyrights with international bodies, and some of which we have rights to adopt and to an extent modify these standards, which is referred to as exploitation rights. But these standards are available to the market at a particular price, which can easily be accessed through our e-commerce platforms. I mentioned our laboratory services. We have about 37 laboratories spanning over a wide and diverse range of sectors. We're also responsible for local content verification. We have a training academy which primarily trains on management system standards. an inspection portfolio, which is consignment inspection. Quite a significant portion of our inspection work is done for government departments, and certification. And certification is basically comprised of two components: product certification, like the SABS mark of approval, and system certification, which is your various management system certification, which we guard and certify both entities within the public and private sector too. So from a global perspective, I think it's important to acknowledge that the key buzzword is around sustainability. The United Nations Sustainable Development Goals, all 17 of them, as South Africa is a signatory to the UN SDGs, there is a significant level of commitment, projects, programs that have been put together by various entities, both in the public and private sector, to drive initiatives and commit to specific targets that we have put forward for ourselves as a global commitment towards 2030 and achieving these targets. So these various UN SDG goals becomes part of our standardization work as well, because we can easily map out the various sectors that we provide standardization for, the deliverables in terms of the standards, and how these deliverables contribute as technical knowledge and solutions towards opportunities and maybe challenges in the marketplace aligned to these global challenges. It is certainly at a national level aligned to our national development plan as well, and this was reiterated from previous presentations. And if we take each UN SDG goal and map it to the national development plan, you would see that they very closely align and articulate to our NDP in South Africa. Moving on a step further is on our DTIC priority sectors. You may have seen a representations of from our colleagues from DTI and Nantombi talking about priority sectors, and we play a very important role in developing standards aligned to the priority sectors. How do we do it? We ensure that these priority sectors become part and parcel and entrenched in our national standardization strategy in terms of the key focus areas. We have to develop technical committees, structure and scope these technical committees to a point whereby we have relevant strategic business plans that have been developed. We have the right relevant stakeholders that are participating in these technical committees. And I must thank the colleagues on this platform who also participate quite effectively, both at a national, regional and international level on the TC on nanotechnology. The guys have been working superbly, and they have made a significant amount of traction around influencing international standardization and bringing it back to South Africa as adoption of these international standards. And we have strategic leadership and influential roles at ISO, IEC, ARSO, which is the African Regional Standardization Organization, AFSEC, which is the African Electrotechnical Commission, SADC-STAN, and in support of the African Continental Free Trade Area. So I just wanted to present a bit of details in the industrial priority sectors, which gives you an idea of the length and the breadth of the types of scopes of standardization. There are sectors, subsectors, and even classified much lower than that as well. So the themes include tourism, agro-processing, which fundamentally has a number of opportunities on nanotechnology opportunities, as pointed out by our colleagues from CSR on hemp and other various aspects of subsectors that could bring about a significant amount of industrialization, services and products for the country in terms of socioeconomic development. The industrial sectors is a little bit more diverse than what has been represented, but this just reflects a few of the key priority areas, industrial areas that South Africa is working on, or the automotive sector, clothing, textiles, leather and footwear, gas, chemicals and plastics. Renewables is a key area of focus as well around standardization, steel and metal fabrication. Mining is obviously quite a significant portion, contributes to our economy as well. And there's a significant element of upstream and downstream technologies, as well as solutions, including beneficiation, value chains that are currently under discussion and implementation. So you've got to have technical solutions that's going to support these advancement of value chains around industrialization. A few of the high-tech sectors, knowledge-based sectors, includes the digital economy. Health economy is certainly a huge area and on our radar in terms of developing right standards and relevant standards. I mean, it had a huge impact as a consequence of COVID-19, and we really were put to the test in terms of how efficient we could work with technical committees, review standards, bring new standards into the fore to address a pandemic. Hydrogen economy, that is certainly another huge buzzword in terms of economic activities, master plans to be developed, and aligned with that, our development of national standards. The green economy, circularity, plastic circularity, these are all talks that we are involved in to establish relevant stakeholders to develop national standards. And it goes on further on the creative sector, defense and aerospace, not so much of activity because it's quite a regulated area. So we don't endeavor into a space where that's it's quite regulated, and there's intergovernmental organizations developing regulations. So we might as well not get into that space to develop standards which might reinvent the wheel. And last but not least, various aspects of the oceans economy. This is just a representation of the type of work and number of standards and technical committees that we have at the SABS. Just as an example, the digital economy on the left of the screen, top column, we have more than 2,300 standards that are published within the digital economy. It also talks to the electrotechnical sector, so it's quite broad. There are about 44 technical committees and subcommittees that work on these projects towards developing these technical solutions. So I'm not going to go too much into detail, but just a reflection of the type of work that we do in the standardization area. I think we all have a common understanding of the importance of standards to our day-to-day activities. And there's certainly not a day that goes by where standards are not at play in any sector of the economy and having an impact on both on actually the three legs of the sectors, which is public, private, and supporting consumerism as well. So standards are basically the state-of-the-art knowledge, and it's a vehicle towards the dissemination of new technologies, new innovative practices. It certainly facilitates trade and support industrialization objectives. And this is why we're here talking about, very important technologies like nanotechnology and transmitting this information on the various aspects from characterization to application to research and last but not least, commercialization opportunities of these impactful solutions. Standards also play a very important role in supporting societal and environmental policies. So we engage very closely with the public sector, government departments, regulators, to ensure that they are aware of these solutions. There's no need to reinvent the wheel. They could use our standards as we have published them, reference those standards to achieve a policy directive and attain a regulatory objective as well. So we try as far as possible to get the public sector involved and creating these documents concurrently with a diverse range of other stakeholders as well. They also provide these documents various modes of conformity assessments that enhance confidence in products, systems, processes, and last but not least, it assists consumers in making important and informed buying decisions. It provides consumer safety. Consumers are involved in crafting these standards within our technical committees, and it provides products and service assurance as well, so that these products are fit for purpose when they are used by the consumers. Key to understand is that, and there's a huge amount of misunderstanding in the marketplace, that standards are regulations and they're used interchangeably. Standards are not regulations. Standards are produced by an authoritative body, which is the SABS, and the SABS is the only body that develops South African national standards. And regulatory authorities, even the public sector entities, should, whenever possible, make use of national standards in their regulatory work or public policy work. And they should, these authorities should endeavor to apply references to the standards to respect the voluntary nature of these publications that we put forward, in the sense that all the documents that we published are not compliance or for mandatory compliance. It's only when they are referenced in a particular, maybe a policy, a regulation, or as part of a procurement contractual objective, then they become by application mandatory. We have in excess of 1,000 standards that have been referenced in national and local regulations, and this is how well the machine is working in terms of standards supporting public policy. And there's a lot of information that we gather as members of ISO in emulating best practice around public policy and use of standards in that area. So as members of ISO, the SABS participates in a very diverse range of technical committees. We are P members of 254 technical committees and subcommittees at ISO, O members of 163. At the IEC, which is the International Electrode Technical Commission, we are P members, which is permanent members of 72 committees, and observer members of 63 committees. And this is where the best practice comes from in terms of contributing and influencing international standards, and thereby reciprocating and adopting these standards as South African national standards, and allow for easy access of these adopted documents to our various stakeholders in the public and private sector. Regionally, we play a very important role in the harmonization of standards in the African continent. So you have ARSO, which is the African Organization for Standardization. I mentioned AFSEC, SADC. These bodies are bodies that are responsible for ensuring that national standards bodies within the African continent work with each other to harmonize standards, specifications, etc., which allow for the easy movement of goods and services within the continent. And this is in support of the African Continental Free Trade Area. So especially in nanotechnology, where the opportunities are so numerous, vast, ever evolving in terms of solutions and commercialization, a technical committee on nanotechnology within the African continent allows for harmonization of standards, and further allows for products and services to move between the markets, and this certainly has a significant impact, socioeconomic impact, on the growth of the African continent, and certainly stimulating a significant amount of intercontinental trade. And this is basically what the objective is, or one of the objectives of the Continental Free Trade Area. On a national basis, as mentioned earlier, we have more than 7,500 standards. We publish on average 250 standards a year. We have about 300 technical committees and subcommittees, and that's how diverse the scope of work is within the various technical committees, serving quite a number of sectors, and more than 1,900 experts that participate, contribute their work on a voluntary basis towards the development of South African national standards. And this was already covered, colleagues. So this is my last slide. So it was more for introducing the topic on SABS TC229 nanotechnology. This has been well covered by Dr. Foster today. Just wanted to highlight that this technology impacts many sectors: energy, water, health, chemical processing, bioprocessing, mining, minerals, advanced materials, which is a significant component, and various uses in manufacturing as well. It is understood that our strategy is to optimally use this technology to enhance our global competitiveness, create sustainable industries, value chains, and commercialization of products and services from this technology, and drive sustainable economic growth. It further promises significant benefits, including enhancements in medical diagnosis, treatments, more efficient energy sources, which South Africa requires at the particular juncture that we find ourselves, cheaper materials, faster and more powerful electronic products, which is referred to in earlier presentations. And there's a wealth of opportunities that can contribute toward the development of innovative energy efficient materials as well, that will assist not only in a global energy crisis, but where we are from a South African context around our energy situation. Of further importance is the effects of specific nanomaterials, which was also presented, particularly nanoparticles, and its impact on human health and environment. And there's a lot of ongoing work on this space in the standardization work as well. My last comment would be on participation on at the SABS TC 229. As much as we have a very wide, diverse range of stakeholders participating, more interested parties represented as association forums, etc., are welcome to participate, either as participating or observer members to come in, and we will have a much more broader and inclusive discussion and development of relevant standards at the SABS around this particular technology. Chair, I would stop there at this particular juncture, and thank you for the opportunity once more to just give a few introductory remarks on the role of the SABS on standards development. Thank you.
Thanks, Sadvi, for the presentation on the role of standards in South Africa. We are now moving on to the second last item, which is question and answer session. If you have any questions, you may raise your hand and then we will attend to that. And the speakers will also be ready to respond to any questions that will be asked. There is also a Q&A button at the top of the screen. You can type your questions there and the speakers will be able to respond to the questions. I've already checked. I saw one question there and the speaker had already responded to the question, which is covered. So if you also have more questions, you can type there and the speakers will respond. But alternatively, you can raise your hand and then we will have your question taken and be answered by the relevant speakers. Any questions? Are our audience still here, Bjorn?
Yes, they are. There's about 70 people here. There's a Johannes. I can, if you want, I can do it, set it open so I can allow him to talk.
Yes,
Johannes.
please, Bjorn.
Johannes, the mic is on, and I'll allow camera as well.
For
for it, Johannes.
presentation. Okay, thank you all for this good presentation. I'm very happy. I know SABS. I'm from Ethiopia and I've been familiar with SABS as we have your colleagues coming to audit, you know, our what you call industries. I want to ask about this CQI and what you call this Bureau of Vitas. Is it under the South Africa Bureau of Standard, or in which category? Is it local company within the South Africa? I want to know this one. Thank you.
Sadvi, would you respond to that?
Thank you for that. So I'm not too familiar on CQI and the acronyms, but let me answer it in this way, that there are a number of certification bodies that are operating in South Africa as well. And I thought I heard you mention Bureau Veritas. So there's Bureau Veritas is a certification body. The SABS is a certification body, SGS, and the likes, etc., that participate on a commercial basis and have a model of certification systems and portfolio of certification activities in any country. Some of these certification bodies have a global footprint. Some of them have a national footprint. So we generally don't have any association or affiliation or partnerships with these certification bodies. So SABS, to your point, your question may be, does SABS recognize these certification bodies or accredit these certification bodies? When it comes to accreditation, it's SANAS who is responsible for accreditation and deeming these certification bodies competent, but some of these certification bodies are multinational, so they are accredited by their home country, and they have been given a license to operate on a multinational footprint perspective. So there may be opportunities to collaborate on new on schemes and how we work together, but at this stage there is no collaboration. It's more of a competitive environment between the certification bodies and including the laboratory infrastructure entities, test labs within any country for that matter. I trust I've provided some clarity to your question.
Yeah, you have, yes, you have given me a good, what you call, reply, but I want to ask even more, if you allow me. Can
Yes, Johannes, yes, you can go ahead.
Yeah. Do you have any like office out of South Africa, like for instance in SABS, others operating in your soil, and do you have like office in some countries so that you can have like you know, many customers? Like it's a competitive environment, in fact, so you need to have you know, reach out to many African countries. I'm very proud with these SABS because there was no company operating in Ethiopia at that time. You know, it was around 20 years ago. So SABS, you're like Bruce, if you know, who used to come in Ethiopia to audit, you know, some companies. And I know they are coming to Ethiopia, but they do not have office here. This will be an opportunity. The other question is, will you provide a training for this someone who are interested to be, you know, lead auditor, and you can just, you know, logistically it is feasible. For instance, if you want to audit any company in Ethiopia, that person whom you are, you know, certified can support you in auditing companies locally. Thank you.
Sure, thank you. So what Johannes, I think it'll be good to get in contact with myself and the head of certification body outside of this meeting, and Fallen will be able to provide our contact details. But just in summary, and for the context of the colleagues on the platform as well. So we don't have a regional footprint in the sense of offices in any of the countries in Africa, or a global footprint in terms of having an office in other areas outside of the continent. You would recall that these are all commercial activities, highly competitive in the marketplace. So the demand will justify the need for establishing offices in the respective countries. In terms of needs for training, I do acknowledge that we have and continue to provide a wealth of training opportunities for a number of national standards bodies in the African continent, and we will continue with that. And where there's opportunities for Ethiopia to come in and make further requests, we'll be able to accommodate that. I think an offline discussion will be a good opportunity to discuss these matters further, and the relationship between training, auditing, the issue of impartiality. I think it's a much broader discussion that we need to have, just to guide you as to what a certification body can and cannot do, and how this comes into play when you also provide training services as well. So thank you for the question, but I think we can go into much detailed discussion at a different opportunity. Thank you.
Thanks, Advi, for the response. Any more questions?
I would suggest people put up their hand, then I can allow them in if they've want to have verbal discussion quick.
Yes, yeah.
Colin, I just noticed there's a question in the chat on liposomes.
Thanks, Hannes. I'll check it now. Hannes, I can't find the question from
It's from New Munaheng.
Neo. Okay, I see it now. Relating to standards for characterization, do we have specific standards for liposomes used in infectious disease nanomedicine? If there are, I wonder what is the biggest challenge for the translation research in South Africa, as there is hardly any product developed in South Africa that get to phase 1 clinical trials. Is there progress in this regard? This is relating to standard. Do you want to take it, Savi, or should I respond?
Thanks, Fallen. I kindly request that you or any of the other colleagues could respond, as I might not have the scope of the detailed technical publications that we have within the scope of liposomes. Thanks.
Okay. And Newa, my response to your question is that we don't have the standard for liposomes used in infectious disease nanomedicines at the moment. And I'm not aware of any developments in that scope of work. We don't have anything that has been proposed to date for development of that specific standard. Newa? Beyond, I'm not sure if Newa is still on the call, just to confirm if I've responded to her question or if there is a follow-up.
Sorry, Neo, that you were not okay. You can go now, Neo. My apologies for that. Neo, you able to talk? I don't get any reply from Neo. I can see she's there, but I can't see a reply.
I hope she had my answer, but
Yeah,
she will
we
let us
all
know
heard
if
you.
Yeah.
Ah, there she says.
I see a hand from Veronica Bion.
Yeah.
Can you allow her to ask a question?
Give me a sec.
Thank you, Fallen. Thank you, Bjorn. Good day, everybody. Fallen, I was just going to respond to Neil to say we do not have a published South African standard for liposomes. However, ISO is working on a standard for liposomes. So the SABS TC229 will look into that standard and see if it's worthwhile to adopt that standard as a national South African standard. Thank you.
Thanks, Vero, for the information. I hope Neo got the message, but if not, I'm sure she will follow up with us. Any more questions before we close the session? Sadvi?
Thanks, Pauline. If I may come in, I think there's been a request for possible applications to technical committees. So maybe we could put a contact person and an email address for requests coming in for participation in our technical committees, and we can engage directly with those emails and respond with the application forms and relevant information in terms of participating to our technical committees. So we could put it directly on the chat box. Thank you.
Okay. Thanks, Advi, for that. Veronica, could you please put the details on the chat box for any members of the organization who would like to join the committee, SABS TC229? Thank you, Vero. Any more questions before we close session 1? I don't see any hands. Okay. We have now come to the end of the morning session, and I would like to thank all the speakers for taking time to speak to us today on the very important topics around nanotechnology. Looking at the time now is 11:38, and we'll take a break, which was planned for 11. We are like 38 minutes late, which is still fine, I guess, because we'll start the next session at 1. So we will have an hour and 20 minutes break. Then we will start our next session at 1 o'clock. I hope that will be fine with everyone, because we really want all of you to be back for the next session, which will start at 1.
Thank you.
Okay.
Thank you all. See you later. Bye.
See
Thank
you
you
at
for-
1. Thank you. Bye.
Thank you.